increase it. Okay, so I mentioned that the sun's energy, and actually anything with a temperature, radiates energy in the form of radiation. And radiation is transferred in energy through the electromagnetic spectrum. So this is an image here of the electromagnetic spectrum, and the wavelengths will be related to the temperature at which objects radiate their most of their energy. So there's a couple components to this image here that's really cool I want to point out. One is here, this temperature thermometer. Okay, it has Kelvin and Celsius. We're going to talk about temperature soon. And this is basically, this is hotter over here. This is a squiggly line, not a negative. Okay, so it's about 10 million degrees Celsius, 9,000 degrees Celsius, and then we go minus 173, minus 272. So this is kind of absolute zero, which is something that has no temperature, so it's not radiating. So this is cooler over here. So what I want you guys to notice is that the hotter something is, the shorter the wavelength. And the cooler something is, the longer the wavelength. And when I say wavelength, this is what I mean. So if we have a wave like this, the wavelength is going to be measured either from crest to crest or from trough to trough down here, and they should be the same. So here you can see it's a very short wavelength, whereas here it's a much longer wavelength. And if you're wanting to, one of the things I like about this image, if you want to understand what they're talking about in terms of wavelength, like how actually how big are these wavelengths, this is a really cool figure, because it says these smaller wavelengths would be so small, they would be as small as, say, viruses and bacteria here, or even molecules, even atoms, even atomic nuclei, okay? And then as we get bigger, this is something that we can't see, this small. As we get bigger, you can think of it as like the point of a needle, or as big as butterflies, or as the wavelength would be as tall as humans, or even the Empire State Building and larger. So I just think this is a really great visual to kind of understand that. Here's the takeaway. You don't need to know all these details about what size the wavelength is or what temperature the wavelength is. The main thing that I want to point out here is to understand that the sun is hotter than the earth. And so the wavelength, the primary wavelength of the sun's energy is going to be different than the primary wavelength of the earth's energy. That is just the basic concept that I want you guys to, what I want everybody to understand. Now, most of the sun's energy reaches the surface of the earth as visible light, or actually even the atmosphere. And there's some UV radiation that's ultraviolet, and there's some infrared that comes in too. But most of it is visible light. And visible light, or the visible spectrum, just means the wavelengths that our eyes can actually see. Is that a coincidence? It's not a coincidence. So as life has evolved on Earth, the primary light energy wavelengths that are reaching the Earth and entering the Earth's atmosphere are the wavelengths that our eyes have adjusted to, and that is how we see, and that is how we see colors as well. So you all know the colors of the visible spectrum, I hope. Here's what I want you to know in terms of what you can put in your notes too. So we're going to put the electromagnetic spectrum like that, and we're going to draw in the visible spectrum, which are, everyone knows, is the colors of the rainbow. So you guys know the colors of the rainbow and their order? If you don't, many people have learned the acronym Roy G. Biv as a way to remember the different colors of the visible spectrum and that the order that they come in. So let's put those in there. R-O-Y-G-B-I-V. Okay, so be like that. So R is for red, orange, yellow, green, blue, indigo, and violet. Okay, so that's Roy G. Biv. That's what most of the sun's radiation that reaches our atmosphere and passes through our atmosphere is in that visible spectrum. Then the only other part I want you guys to know about the visible spectrum is what's on either side of the visible spectrum. The electromagnetic spectrum is what's on either side of the visible spectrum. So first of all, of the visible spectrum, I also want you to know this, what side has the longer wavelengths and what side has the shorter wavelengths? Now you can look at this image that I've put over here and look at the wavelengths up here and look at the colors of the visible spectrum here. Red, orange, yellow, green, blue, indigo, violet. Okay. So red, longer or shorter than violet? Red, longer or shorter than violet? It's longer, yeah. So, oops, you should know that on this side, longer wavelengths, and on this side, shorter. Okay. And you can flip this spectrum, by the way. Sometimes you might see a graph where it has red, orange, yellow, green, blue, indigo, violet going this way, and then it'll have shorter over here and longer over here. Okay, just look at the scale the way that they've put it. So I like to draw it this way just for all of you because you probably learned the colors of the rainbow in that order, Roy G. Biv. So longer over here. So these are the only wavelengths that we can see with our eye. On the longer side, we have wavelengths in the infrared. On the longer side, we have wavelengths in the infrared. And remember, longer is cooler. So the Earth and the objects on Earth like us, like humans and animals, give off our radiation in the infrared. And we don't see that with our naked eyes, though we have special technology, cameras, goggles, scopes, so forth, that can see the infrared. So this is used in like war and hunting, and other science applications where you can see the heat, basically, or the energy, the radiation that various objects are giving off, whether that is an animal in hunting or a human in war, and even other objects give off infrared, but they tend to be, if they're not alive, they're not radiating as much heat. Okay, so I want you to know that infrared is on this side of the red. It's longer wavelengths. on this side, we're going to have shorter than violet, shorter than violet. So the wavelengths on the shorter side of the visible spectrum are called UV. UV for ultraviolet, ultraviolet radiation. You guys can see this here, ultraviolet, visible, infrared. So I want you to know those three categories, and that infrared is longer wavelengths and from cooler objects. Then you have visible, and then you have shorter wavelengths in the ultraviolet for hotter objects. Okay, so I'm going to stop there, and we'll talk about what happens when this energy, these wavelengths, enter the Earth's atmosphere.